Okay, so in the previous lecture, we learned the basic of light, and we learned about the wavelength, the frequency, and the energy. And we saw that electromagnetic radiation have a lot of different waves. And for example, on the visible light, if all of them are combined, the one from the visible, we just see white light, but it's composed of a bunch of different wavelengths with different energies of their own. So how does that connect to matter? That's what we're going to be doing here. Here we're going to see how we can understand light connected to matter, and to do that, we have to design a model of the atom. You learned earlier that the atom is composed of a nucleus and electrons. The nucleus is on the center with the protons and the neutrons, and the electrons are all around. And the nucleus is made out of protons and neutrons, like I told you. The proton is positive, the nucleus have no charge, so the nucleus overall is a positive charge, and it attracts the electrons, which are negative. So how do we relate what we learn about the light and matter as we talk about the atom? And for that, we're gonna come up with the Bohr's model. So let's see how that where that comes from. So each element, when exposed to electricity, especially the gases, some of them are gonna emit light. And as you noted on this example, the light that the mercury emits is different in color from the light that the hydrogen emits, which means they have different energy, different wavelengths. And if we take those lights that are coming from those elements and we put them through a prism or something similar to that, like we did with the light that gave us the rainbow, we see that they show a line spectrum. And this line spectrum, we have come to learn that is like a fingerprint for the element. So every time you see this particular line spectrum, you know that what you're looking at is hydrogen. For example, if I am an astronomer and I'm looking at a star millions of miles away from me, and I get that light that's coming through my eyes and put it through a prism, and I get something like this, I can say, wow, that star contains hydrogen. But if I see something like this, I'm gonna say, there's definitely mercury on that star. So each element is displaying these specific lights with specific wavelengths. So the scientists back then, that was like a beginning of the 20th century or mid 20th century, they said, how can we correlate this to what we know, since we've seen different lights coming out of these elements? And they said the only way this can happen is because the electrons are doing something. And they came up with the Bohr models, which is similar to the solar system, with a nucleus and then the electrons going around. And for example, for oxygen, where we have 1, 2, 3, 4, 5 different types of lights or wavelengths, what they said was that means that hydrogen have 5 different energy levels. So if we had different wavelengths, remember that the wavelengths relate with the energy, right? The longer the wavelength, the smaller the energy. So level 1, which is closer to the nucleus, it would be the one with the least amount of energy. And if you haven't seen the opening video for week number 10, make sure you watch that, because that's going to make this so much more understandable. So level 1, which is the closer to the nucleus, will be the one with the least amount of energy, which means it's the one with the bigger wavelength. So we would say that this is probably level 1. followed by, actually, sorry, this is level 1. Then we have level number 2, which if we follow the energy, it gotta be this one. And we can do the same thing with level number 3. And once more, I can see that I'm off by 1. Let me start doing this again so I can see it better. So this will be level 1. This will be level 2, level 3, level 4, and level 5. So level 5, which is the one with the bigger amount of energy. Remember, the closer you are to the nucleus, the more stable you are, so the least energy you have. So this will have to be level 5, level 4, and level 3. So if we visualize the atom where the electrons are distributed at different levels, when the electrons move between levels, they will have to absorb energy to go up, and when they come back, they will release energy. That energy is going to have to be released as a photon, and if you happen to be around, that photon is going to hit your eyes, and you will see something. On this case, you probably have a machine, and the machine detects that photon. So what we're doing is we're relating the fact that we are getting a fingerprint of the element because of the different wavelength, and relating that to the position where the electrons are going to be. And something that you can look at, which is basically a logic, level number 4, for example. So level number 4 is smaller than level number 5. Everybody can see that, right? So that means that you can have more electrons on level number 5 than what you can have on level number 4. So with that said, you can imagine that on level 1 is where you have the least amount of electrons. So this will be something that would be worth memorizing. For level 1, and we're going to call that level n equals 1, the maximum amount of electron is going to be 2 electrons. For level 2, that's going to be 8. For level 3, that's going to be 18. So that's nice to know. That's going to help us later. So the only way we can relate the fact that the elements give us a fingerprint as a line spectrum if we assign electrons to different energy levels. And that's how the Bohr's model was born. And this is what I was saying before. So for you to be able to see that there's light coming out is because an electron is returning from a higher level to a lower level. Higher level, we have higher energy. The lower level, we have a smaller energy. So for this to make it to that, it's going to have to release energy in the form of a particle of a photon. And the photon have energy that is related to the wavelength. And that's what we see here, the wavelength. Remember, wavelength is measured on meters, right? So these are nanometers. So this is the one with the longer wavelength. So the smaller energy. This is the one with the smaller wavelength. So the higher energy. So let's see if that match. So this one is coming from this energy transition, while this one is coming from this energy transition. Just on the size of the distance that the electron has to travel to come back, you can see that going from 1 to 5 and then coming back is a lot more energy than going from 3 to 2. So that's how we can start relating that. So for an electron to go to a higher energy level, it will have to absorb energy, but it will immediately come back to be more stable closer to the nucleus. And to do that, it would have to release a photon. So keep that in mind. So let's do a problem like this. Make sure we understand the Bohr's model. So remember the Bohr's model, you have the nucleus on the center, and then you have a specific quantized energy levels where the electrons are going to be. The farther the energy level is from the nucleus, the higher the energy. The closer, the lower the energy. Lower energy, more stable. So if you give energy to that atom, the electrons will absorb it and go up to a higher energy level, or immediately will try to come back to be more stable, and to come back, you have to release that energy. The energy will be released in the form of a photon, which is a packet of energy with a specific wavelength. So this problem, two of the emission wavelengths in hydrogen emission spectrums are 410 and 434. One of these is from 6 to 2, and the other is from 5 to 2. So obviously, 6 to 2 is going to be bigger than 5 to 2. So higher energy, which means lower wavelength. A small energy, higher wavelength. So from 5 to 2, which is the smaller energy, you will have to have the one with a bigger wavelength. So 5 to 2 is going to be 434, while 6 to 2 is going to be 410. All by relating the fact that the smaller the wavelength, the higher the frequency, the bigger the wavelength, the smaller not the frequency, the energy. The bigger the wavelength, the smaller the energy. And if we want to represent it with the Bohr's model, you will have your nucleus with level 1, level 2, level 3, level 4, level 5, and level 6. One of them is going to go from 6 to 2, and the other one is going to go from 5 to 2. So this is the biggest one, the bigger energy. So with that information, you should be able to do daily work 9.4. And with that for this course, that's all we need to be able to understand the Bohr's model. If you were taking the chemistry for science majors, we will be doing a lot of formulas and actually calculating the energy for each transition. No need to do that in here. We're just kind of understanding the relative strength due to the wavelength. And with that, how we got to design an atom with the Bohr's model. So if you notice the Bohr's model, the one I showed you here, It looks kind of like a solar system, like I told you before. That's what we call those orbits. But that's, when I show it to you like that, that's a flat representation. If you look around you, everything is 3D. So we had to understand that model on a 3D frame of mind. So let's do that. So once we do that, then we can move to the next topic, which is understanding the quantum mechanical model. But let's see first, why do we need another model? Well, here's the reason. The Bohr model is important because it provides a logical foundation to the quantum mechanical model, basically implying the quantum mechanical model comes after the Bohr model and is a better model. So the Bohr model is lacking. And we also see that the Bohr model it allows us to understand historically the development of the scientific understanding. This is what this is saying is the Bohr models have problems. So using the Bohr model, every one of those lines I can predict it, which means I have a theory that matches reality. So I can use the Bohr models with hydrogens and it works perfect with what we see on the line spectrum. The moment I move to helium and everything else, the Bohr models do not work. So this is a very faulty theory or a very faulty model. Only works with one element out of 118. However, it allows me to explain the absorption of the electron, the release of the photon, the different energy levels, and so on, but only works with hydrogen. So this is not a good model. We cannot use this. So what we said was, well, the Bohr model on a 3D world, it would be something like this. So every time you see this model, be aware that that's not true. That model is not a good one, only works for hydrogen. The only reason we still use the Bohr model is because it allows an understanding, a very basic understanding. Only works for hydrogen, doesn't work for anything else. And we had to be able to use models that allow us to make predictions. And the prediction had to match the reality. So what we did, and I'm taking credit where I don't deserve it, what people before me did was they said, well, we cannot be thinking about electrons kind of moving around the nucleus like if they were planets around the sun. We don't even know where the electron is at any time. The only thing we can talk about is the probability of finding the electrons. So we came up with probability diagrams. So instead of having this orbit like the one I'm drawing right now, what we have is not an orbit, but the space inside that orbit. So the space inside that orbit is where we say that we most likely will find the electron. So we cannot talk about the electron in absolute terms. We can only talk about it in terms of probability, in terms of its location. So we do a probability diagram, and based on this probability diagram, the electron is going to be most of the time around here. You see how much then is over there. So we can find it on the perimeter, but in very rare occasion. But there's a possibility we can find it there. You can even find it probably over here in a very, very small possibility. So from now on, we're not going to see the location of the electron like a solar planet, like on the Bohr model. What we're going to see is a probability diagram. And like the textbook told you, the best way to understand this is imagine that you have a super camera that can take pictures of the electrons, and you take a pictures a picture every nanosecond. So there's only 1 or 2 electrons there. You take a picture every nanoseconds. After you take 1,000 pictures, you overlap all of them together, and it shows you where all the different places where the electron was located. And that's more or less the closer way to understand this. Every single dot here is a different period of time where the electron was at that point. But it could be anywhere, but we tend to find them most of the time kind of closer to the nucleus because negative love positive. So we had also to understand that this is a 3D version, so it's not like a flat circle, it's more like a sphere. So on level 1, you will find something like this. And then you will have level 2 surrounding level 1, 3D, like a sphere inside the sphere, like the Russian dolls. And then you will have level 3 encasing, not encircling, encasing level 2 and level 1. And we're going to call those 1S for level 1. And we call in this type of diagram, this one that looks like a ball, a sphere, we're going to call it S. Then we will have level 2 and level 3. Level 3 will have the higher energy because it's farther away from the nucleus, right? So this is a way to see it. If we cut it in half, it's like a ball inside a ball inside a ball. And all those areas there are where the electrons can be, but noticing that there's like a gaps in there. And those gaps are going to correspond with the distance. Remember on the Quantum for Babies story that, like I told you on the week opener, the electron can never, ever, ever be here. It has to be on the level. It cannot be in between levels. That would be like if you're going up the steps, it would be like standing in between the steps. Impossible. So that's how we're going to understand the position of the electrons. Not like an orbit going around, but like a probability diagrams, where we can see where we expect the electrons to be most of the time based on probability. And it's going to be 3D. And we're going to call those orbitals. So wherever the electrons are, that area where the electrons can be, we're going to call those areas orbitals. And quantum theory gets complicated. So the sphere is really easy to understand, but the electrons are going to take other shapes for the areas where they can be. So this is what we're going to call the S orbital, which looks like a sphere. Remember, it's kind of 3D. But we're also going to see something like this. We're going to call this the p orbitals, and it could be on the x-axis, it could be on the z-axis, or it could be on the y-axis because we're covering a 3D space. Then you can have the d orbitals, which are going to be a little bit more complicated. And then you're going to have the f orbitals, which are crazy. So if you can recognize, you don't have to memorize any of this, but if you can recognize an S, a P, and a D, you should be okay. You don't have to be, and if you see something super crazy, that gotta be an F. With that amount of orbitals, we have more than enough space to accommodate all the electrons, even of the last element, which contain 118 electrons. So those are what we call orbitals, and they're going to be S, P, D, and F. It would be good to know or memorize that the maximum amount of electrons on any orbital is 2 electrons. the maximum number of electrons any orbital can take is 2 electrons. For that reason, you can put 2, 6, 10, and 14. And at this moment, you should be saying, oh, wait. You just told me that the maximum number of electrons is 2 electrons. Where are you getting 2, 6, 10, and 14? Well, let's look at these drawings again. Notice that on the 3D space, if you have a sphere, there's only one way to put it. You cannot put a sphere upside down or sideways. It's just a sphere, only one. So the s orbital, which is the sphere, is only one orbital. So therefore, 2 electrons. However, the p orbital on the 3D space, you have one on the x-axis, one on the z-axis, and one on the y-axis. Each one of them can take 2 electrons. So that's why P is 6 electrons. Same logic follows for D. There's 1, there's 2, there's 3, there's 4. So there's 5 different arrangements where the electrons can be. And you may wonder, why do we have so many different arrangements on different axes, X, Y, Z, and all that kind of stuff? And the reason is electrons are negative. Imagine putting 118 electrons around the nucleus, and every single electron wants to be close to the nucleus because the nucleus is positive, but they hate to be close to other electrons, and you have 118 of them. What they do, they accommodate themselves in different areas where they can survive without ever having to cross with another set of electrons. So the orbitals are going to allow me to put the electrons there, avoiding all the other electrons. That's what you have the piece like that, or across on this way, or top to bottom on this way. So 6 electrons, and the most they see with themselves is only one more electron, maximum 2. They don't see the other 4. They never cross paths with the other 4. And as you can see, the D have 5 different orbitals. That's what you can have 10 electrons maximum, because there's 2 electrons per orbital. And the D is going to be 1, 2, 3, 4, 5, 6, 7. So therefore, 14 electrons maximum. It wouldn't hurt for you to memorize this here. Maximum on X is 2, maximum on P is 6, maximum on D is 10, and maximum on F is 14. So now how can we do a problem like this? Sketch the 1s and 2p orbitals. So 1s is going to be like a ball. Imagine that's 3D. And 2p orbitals and p orbitals are going to be, one goes like that. Remember, we're not moving the electrons along these lines, right? The electrons are somewhere in there and in there. So it's a probability map. So we're going to have one like that, one like this, and one coming toward you, and the other part is going behind the plane. So this is what we call the X. This is the Y. And this will be, my Z. How do the 2s? So we're going to compare now the 1s versus the 2s. So if this is the 1s, the 2s is going to be kind of swallowing the 1s, so it's going to be on the inside. So this will be the 2s. And the 2p, I can say that this is one of the 2p's, and the 3p is going to be something like that. Because remember, the bigger this number, right, the farther they are from the nucleus. So with that said, you should be able to answer this question, connecting everything you have learned so far. And you should also be able to answer this question and this is probably enough at this point to understand the basics of the quantum mechanical model. Why do we call it the quantum mechanical model? Because every energy level have a given amount of energy. That's what quantum means, a specific amount of energy. And with that, we come to the end of this part. When we come to the next part, we're gonna see, okay, I don't wanna be doing drawings all the time, so show me how to write that on a better way, something that can help me communicate without having to do so many drawings. So that's what we're doing when we come back to part C. So see you later.